gas whispers from below. If the ground is the body language, the gases are the breath, quiet, warm, and full of clues. Start with carbon. CO2 seeps out of Yellowstone year-round, but the pattern has been changing. Survey teams laying plastic chambers over meadow soils kept finding bigger hotspots, patches that weren't there on older maps, where meters tick up and tree roots brown from strangled oxygen. On cool mornings, you can see it in the way fog hangs odd in low spots, thicker than it should be. A ranger calls it ghost air. The chemistry calls it an expanding, diffuse, degassing field. The ratios matter more than the totals. Helium has flavors. Most of what we breathe is crustal, but a small share, helium-3, carries a mantle signature. When the 3/4 ratio nudges upward, even a little, it's a fingerprint of deeper input. In several basins, those ratios bent toward mantle values at the same time CO2 flux grew. That pairing is hard to blame on boiling old groundwater. It says the system isn't just exhaling yesterday's steam. Something fresh is pushing from below. Then there's sulfur's quiet. People expect to smell rotten eggs if magma climbs. In a dry, open system, you would. Yellowstone is neither. It's wet, fractured, and capped. SO2 dissolves into water, reacts into sulfate, gets trapped before it reaches the sky. So when the official line leans on no sulfur spike, they're trusting a brake that's built to hold, until it doesn't. Meanwhile, carbon slips through early, faster, farther. If you want the early whisper, you listen for CO2 and helium, not the shout of sulfur. Microstories accumulate. A hydrologist sampling the fire hole noticed the river's dissolved inorganic carbon jumping a few percent above its usual swing, right as an upstream meadow's CO2 flux map added new red pixels. The same week, a cottonwood stand at the edge of that meadow yellowed from the bottom up, a classic suffocation pattern. In her field book, she wrote 2 words underlined twice: fresh input. Another, a pilot with a nose for thermals flies a fixed-wing pattern over West Thumb to chase down a routine gas transect. 2 hours before takeoff, the run is paused for internal review. It's not the first time. He logs the cancellation, adds a question mark, and goes home. 3 weeks later, the same. Transect gets a green light, but by then the wind patterns have shifted and the lake's thermal skin has cooled. The data are clean. They're also late. Gas doesn't move alone. It drags water chemistry along. In the Madison River, a summer profile picks up slight increases in bicarbonate and a trace of chloride where a cold tributary should have diluted everything. Not a headline, but a nudge. The lab report's footnote mentions isotopes trending toward magmatic CO2. Small but coherent, the analyst writes. That phrase keeps showing up. Meanwhile, trees tell their own version. At Norris and near the North Rim, foresters flag new mortality patches, irregular ovals where conifers browned in clumps. Soil probes beneath them read high CO2. The pattern spread downslope over a couple seasons, not with beetle galleries or drought stress, but with invisible gas pooling in hollows on still nights. The park's botanist filed it as physiological stress likely due to soil gas. The volcanologist filed the map. The absence of sulfur remains the puzzle that comforts. It shouldn't. At Campi Flagre and Rabaul, similar wet caps muted SO2 until systems unzipped and the signal jumped from silence to scream. Yellowstone's cap is broader and colder, a champion sulfur scrubber. If you're waiting on that scent to declare fresh magma, you'll be late by definition. Then there's a detail most visitors miss: bubble size. In a few pools that used to simmer gently, bubbles grew fatter and fewer, classic CO2-rich degassing. Boiling water makes chains of tiny, frantic pearls. Carbon makes heavy beads that pop with a soft thud. A tech at West Thumb filmed it, slow motion, and laughed in the lab. "It's like the system switched soda brands," she said. Her supervisor nodded, then added the clip to a training deck on gas signatures. All these threads, ratios, rivers, roots, bubbles, point in the same direction. Renewed input from below, not just old water finding a new crack. The timeline attached to that is the part that bites gases outrun magma. CO2 can be the first postcard from an intrusion we won't see on a satellite for months. That's why canceled flights and delayed field runs matter. The early signal is perishable. Impact lands quietly. The more domains that light up, meadows, river chemistry, isotope ratios, the tighter the plumbing feels. Pressure couples faster. Hydrothermal caps stiffen, then creak. Valves that held for decades start to chatter. If gas says new fuel, it's telling you the engine's throttle just opened a notch. And if that's true, the next voice that rises won't be a whisper. It will be the map of tiny earthquakes learning new routes through rock. The swarms that drew a map. If gases are the whisper, swarms are the handwriting. Messy loops that keep returning to the same alphabet. Yellowstone's earthquakes aren't the cinematic kind. They come in clusters, hundreds of tiny taps that migrate like a slow scribble across a desk. On a quiet week, analysts see scattered pops. On an interesting week, the dots connect into lines that drift, stall, and turn, like someone testing doors in a dark hallway. This isn't a tomorrow problem, but it is a this decade decision problem. How we read these lines now sets what we can protect later. West Thumb does one kind of anger. Under the lake's cold skin, low-frequency events gather in bunches. Soft thuds more than snaps, stacking at depths that match hydrothermal vents on the lake floor. When these pulses come, hydrophones pick up a faint, bassy tremor, as if the basin is humming to itself. Boiling? Maybe. But those events sometimes step outward along a known fault, and their spacing looks tidy, meters apart, seconds between, like fluid pushing through a zipper. That's a pattern you see when gas finds a new seam. Madison Valley has a shorter fuse. Its swarms tend to be brittle and hurried. Sharp microquakes marching along northwest lines that echo old breaks in the crust. They start compact, then fan, then go silent, the way a dike might test a rock and back off. You can overlay 3 years of these and watch a ghostly ladder lean against the caldera's edge. Norris is the one people watch with a hand on the door. Its swarms come layered, high-frequency cracks at shallow depth. Then hours later, a faint roll deeper down that doesn't show up in the first filter. The timing feels like a pressure wave arriving late. In the days after, small vents migrate, a pool turns milky, and a trail closure sign appears with a polite tone that doesn't quite hide the urgency. Norris is a governor on the system. When it stiffens, everyone pays attention. These aren't isolated pots. Over a few seasons, the swarms outline connections. A run at West Thumb would fade just as Madison lit up. 2 days later, Norris would answer with a low, even murmur. It looked like a pulse moving through a network. Deep input pressurizes under the lake, fails to break there, tracks along the ring fault toward Madison's fractures, bleeds, then sends a longer wave toward Norris's cap. Earthquakes drew that map before any press release framed it. A night shift analyst named Ramon heard it first. He was new enough to still be excited by cataloging, old enough to trust his ear. At 2:13 a.m., a stack of small events under West Thumb started to repeat, a beat with a little swing. He pulled a spectrogram, saw energy drift from 1 to 3 hertz in a stair-step pattern, and pinned the window. An hour later, a similar stair-step appeared under Madison, phase shifted, a hair tighter. He marked that too. By dawn, Norris was printing a soft, long-period tremor that matched the same slope. He slid his chair back and said to the empty room, "It's talking to itself." In the morning meeting, the note went into the log. It didn't change the summary, it changed how a few people listened. Low-frequency events sit at the center of the argument. They can be boiling in fractures, magma moving, or both. In a place as wet as Yellowstone, separating water from melt is a headache. But when you get migrating swarms that follow a fault trace, show a clear progression of depths, and end with gas anomalies or a pond's chemistry flicking toward chloride, you start leaning away from just steam. Fluids are moving. Some days, the fluids carry the signature of new heat. The migration speed matters. Dikes advance at meters per minute to meters per hour. Hydrothermal fronts move slower. Yellowstone swarm trains often creep at rates that sit between too fast for pure pore pressure diffusion, too slow for a clean dike racing. That middle lane is the coupled case. Gas-rich fluids leading the way, fracture tips preparing space, melt staying back but sending pressure forward. By the time magma faces decide whether to follow, the hydrothermal system has already adjusted, sealed some cracks, blown others, and left a breadcrumb trail in quake times. Patterns repeat. Summer 2008 drew a diagonal from West Thumb to Madison in 3 days, with Norris humming on day 5. Winter 2017 did the same run shorter and tighter, capped by a small hydrothermal blast near Emerald Spring that never made cable moves. In both cases, CO2 meters in meadows along the line ticked up in the week after. That's not a coincidence, that's plumbing. One detail that unsettles field crews: swarm density spikes right before rate changes in the ground. The 2-day GPS hops from Section 3 often land on the back of a 12 to 24-hour period where tiny events pile up like sleet. Then the swarms go quiet as the ground takes the step. It feels like a head fake, but it's the opposite. The brittle crust protests, then yields, then rests. Watching that. Cadence turns swarms from noise into timing marks. None of this says tomorrow, it says connected. The old picture of isolated basins, Norris as its own beast, West Thumb doing lake things, Madison doing fault things, misses the way pressure finds paths. The swarms drew a map of valves and hallways. They also taught a hard lesson. The system can reroute fast. An intrusion that fails under the lake can show up at a hillside vent 2 days later, and the only hint in between is a staircase of low rumbles most people sleep through. Impact is simple. A connected system couples signals, rate changes in ground deformation, gas whispers in meadows, and migrating swarms start to land closer together in time. When that happens, your warning window narrows. The map that swarms drew isn't just a diagram, it's a stopwatch with jagged edges, and it pointed to the next reveal. Rocks cooled long ago, telling us the clock doesn't tick the way we were taught. The 20-year recharge surprise. Rocks that cooled 100,000 years ago shouldn't have anything urgent to say. Then geochemists started cutting them thin and timing the crystals inside like stopwatches. Zircon and feldspar don't lie about heat. They grow when melt is present, they stop when it cools, and the diffusion profiles along their rims keep a memory of the last warm breath that touched them. In lab rooms that smell like ethanol and patience, those profiles started whispering something awkward. Assembly can be fast. Not geologic fast. Decades fast. You can almost smell the lab air, acetone, warm instruments, while a laser walks a rim that records a few hot years that changed everything inside the mush. Here's how the clocks work. Zircon likes hot, silica-rich melt. When a reservoir heats up, new zircon grows, and its uranium lead age pins when the melt was eruptible. Feldspar, loaded with elements that move at known rates, records how long it sat at certain temperatures before the system changed. Put enough crystals on a spreadsheet and you can map pulses of heat. At other calderas, Rabaul in Papua New Guinea, Campi Flegrei near Naples, those pulses lined up tight against eruptive episodes. The kicker wasn't the explosion, it was the ramp. Crystals saw decades of rejuvenation before events that changed skylines. Picture a diffusion profile like tree rings squeezed near the bark. Tight bands that only form if the last warm-up was short and intense. Yellowstone's crystals got the same treatment. Old studies assumed long, steady storage. New work reread the rims and diffusion halos and saw spikes. Narrow bands where elements migrated over distances you only get if the melt got hot and stayed hot for years to tens of years, not millennia. The zircon ages clustered suspiciously close to known lava and ash units. The feldspar zoning said the mush wasn't just a pantry, it was a kitchen that could be turned on quickly. Call it the mush problem, flipped. In a big silicic system, most of the volume is a crystal network with melt threaded between grains, like snow with slush in between. That mush is stable until you add heat or volatiles. A small intrusion from below, a few percent by volume, can raise temperature a handful of degrees, lower the melt's viscosity, and suddenly the grains are swimming, not locked. That's the switch. You don't need a fresh ocean of magma, you need a thermostat nudge. The crystals record that nudge as a sharp-edged zone you can measure with a laser. A case study helps. At Rabaul, the 1994 eruption followed about 2 decades of unrest, uplift, gas, and quakes that looked annoyingly like background until it wasn't. Zircon rim ages and diffusion models later showed a rapid assembly window in the decades prior. Campi Flegrei's recent decades of bradyseism, slow rise and fall, come with geochemical hints of quick remobilization episodes. Yellowstone isn't Naples. It shares the physics. Reinterpreting Yellowstone's crystal data doesn't predict a date, it shrinks a category. Recharge used to mean thousands of years of steady drips filling a bathtub. Now it can mean years to decades of pulses turning a slushy bowl into something that can move. Couple that with the deformation bursts and the gas ratios we've been hearing, and the timeline stops feeling like inheritance and starts feeling like planning. A micro story from a lab bench. A grad student named Kieran was running secondary ion mass spectrometry on zircon from a late rhyolite flow. He kept getting rim ages bunched within a human lifetime before the eruption, the kind of clustering you expect in basalt, not in a giant silicic system. He reran standards, checked for lead loss, swore at the machine, then sent the plots to his advisor with a subject line that read, Please tell me I'm wrong. The reply arrived an hour later. You're not. Start writing. This is the part that unsettles meetings. If mush can flip to mobile on decadal scales, your hazard frame moves into policy time. Lifetimes.
Infrastructure cycles. Insurance windows. It means we'll know centuries ahead. Comfort collapses into we'll see coherent signs and have to choose within the span of a career. It also means you can miss the window if you only watch for sulfur and cones. There's another twist. The first phase of that switch is quiet at the surface. Heat and volatiles percolate up. CO2 takes the early train, helium ratios lean deeper, deformation rates stutter, swarms migrate. SO2 stays scrubbed. The crystal clocks are telling you what the system did last time it got ready. Our instruments are telling you it knows how to do it again quickly. Skeptics point out the obvious. Yellowstone has been restless without erupting for a long time. True. But the question isn't, will it erupt tomorrow? It's, how fast can it build the conditions to? Decade-scale assembly fits inside a human spreadsheet. It also fits uncomfortably well with uplift pulses that move in days, gas fields that expand over seasons, and swarms that draw new hallways in weeks. So who manages the throttle if the engine can spool fast? That's the political question we'll get to. The scientific one lands first. Stop treating recharge as a glacier. Treat it as weather. When the crystal clocks and the present signals rhyme, you don't count from the last big blast. You start a new timer and admit it might be set in years, not eons. The meetings, memos, and messaging. It starts in rooms with bad coffee and good intentions. Tuesday, 9 a.m., an interagency call that always runs long. Evo scientists, park leadership, state emergency managers, a tourism liaison who keeps reminding everyone about peak season optics. The first slide is the dashboard we've been living with. Uplift curves, swarm counts, gas ratios with cautious error bars. The second slide is language, unrest or variability. Someone says unrest triggers policy thresholds. Someone else says the data don't meet the bar. The volcanologist at the end of the table stares at her notepad and draws two circles, one labeled physics, one labeled phones. The tension has three roots. Scientific uncertainty, no one wants to cry wolf. Political pressure, don't spook bookings. And budget constraints. Wording can tilt grants and overtime. The phrasing battles never look dramatic from the outside. They land as footnotes, consistent with past variability. No immediate hazard indicated, ongoing evaluation. Inside the room, the edges are sharper. A seismologist points to short, sharp rate changes on a GPS plot and says, "This is not seasonal." A hydrothermal specialist counters, "It can still be hydrothermal." The emergency manager asks a practical question. If I use the word unrest, what happens next? Phones, budgets, headlines, those are the aftershocks. Grant cycles hum in the background like an air conditioner. You only notice when it shuts off. A junior researcher practicing her briefing is told to avoid rapid mobilization unless she can anchor it to a peer-reviewed study in the last 2 years. She can. The supervisor nods, then suggests swapping in recently recognized processes. It's not just caution, it's survival. Soft language travels farther without setting off alarms in offices that hold purse strings. This is how a cushion becomes, to outsiders, a cover-up. The mix of caution, politics, and budgets sands off edges the public should sometimes see. Tourism boards sit at the edge of these calls, sometimes silent, sometimes not. A county official clears his throat and says a bureau is fielding cancellation emails after a blog ran unrest in a headline. We need to balance accuracy with community impact, he says. He's not wrong. His town's winter business depends on the kind of calm that melts easily. A ranger who spends nights near Norris hears that and thinks about the pressure gauge that jumped last week and the trail closure she posted with a smile. Then there's the data that doesn't land when it should. A request goes up to embargo, a new gas transect, pending quality control. The internal justification. Calibrations drifted on a sensor during last month's storm. The ratios need a second lab to confirm. The external impact, no numbers in the next update. A field team grinds teeth because the patterns are clear, even without a second decimal place. CO2 is expanding into meadows where it didn't pool before. Helium ratios aren't shrugging off the mantle nudge, but the memo says defer, and defer buys peace in inboxes. Call the driver what it is.
Institutional caution reinforced by political optics and budget fear. A resignation letter circulates in draft, never sent. The author is mid-career, tired of sentence surgery. She writes that risk communication has been bent by non-scientific incentives, then deletes the line and saves the file as notes. She stays. Most do. They still file the sharp plots in internal folders with names like Watch Later. A micro story from a hallway, after one.
Call an analyst corners his boss with a printout of a swarm spectrogram. The staircase Ramon heard. If we say variability again, we're going to train the public to ignore cadence, he says. The boss rubs his eyes. We can say variability trending atypical, he offers. It's a compromise that tastes like lukewarm coffee. The analyst adds a footnote in the monthly blog anyway. Rate changes matter. It survives copy edit. The victory is small and real. Pressure doesn't just build underground. A state senator phones the observatory and asks for a briefing to prevent panic. The meeting slides get one new bullet. No evidence of imminent eruption. It's true, and it becomes the headline, quote. The part about episodic intrusions and decadal assembly stays in the second paragraph that most readers don't finish. A local paper runs with all normal. A podcast cuts the caveats and posts, scientists say calm down, clicks run their course. The people inside the machine aren't villains. They're triaging attention. A comms officer drafts two versions of an update, one with unrest, one with variability. She knows which one will go up. She also knows she can slip in a graph that shows acceleration, not just totals. The caption is careful, the picture is not. It's a quiet rebellion in pixels. All of this matters because the clock we've built is made of words as much as instruments. If you call a burst variability 5 times in a row, the 6th time your warning sounds like a rerun. If you embargo early whispers in the name of polish, you give up the lead that carbon buys you. The physics isn't paused by phrasing. The audience is. So we name the forces plainly: uncertainty, politics, and budgets. And then we design around them. Strip the spin, and the signal's still there. Rate changes, migrating swarms, gas ratios leaning deep. The next rooms on our tour won't have memos. They'll have maps of reservoirs and conduits and thresholds that don't care about grant cycles. That's where we go now. Past the language, into the magma. 2 chambers, 1 problem. Strip the slides down to the bones and you get this. 2 reservoirs stacked like lungs, breathing through a chest wrapped in fractures. The lower one sits deep, hotter, bigger, fed by the hot spot's constant heat. It isn't a vat of syrupy magma. It's a sponge of crystals soaked with melt, hotter than anything above. The upper one, closer to the surface, is cooler and stickier, a crystal-rich mush that's most of the time too locked to move. Between them, a messy web of sills, dikes, and faults. The hallways that decide where pressure goes when something nudges the system. Seismic tomography gave us the first honest shapes. Geophysicists fired waves through Yellowstone and listened for the slow patches, zones where seismic energy dragged because hot, partially molten rock smothered the signal. Early images looked like cloudy puzzles. Newer arrays sharpened the picture into 2 broad, low-velocity bodies, a deeper, thicker reservoir and a shallower, patchier one. Then came the hard translation. Melt percent in those images isn't a lake of liquid. It's the fraction of liquid between crystals. 10 to 20% melt can be mobile if you warm it a bit. 30% can act like a slurry. At 40, you've crossed a threshold where rock starts to behave like a fluid, if pressure helps. That's where thresholds matter more than averages. Yellowstone's upper reservoir doesn't need to be a swimming pool to be dangerous. It needs connected pathways of melt, what petrologists call permeability, and enough gas exsolving to push.